finish this problem to find out how far up the firefighter can climb, let's apply the conditions of static equilibrium, which say that the net torque on the object, the net force in the x, and the net force in the y are all equal to 0 because the ladder is not moving, the ladder is not slipping. So we'll start with our condition for static equilibrium for the torque, which is that the net torque of the ladder is equal to 0. So we'll say that the sum of the torques equals 0, which means we're going to add up the torque in the table here, minus L times normal force at the wall times cosine 60 degrees, plus L over 2 times mass of the ladder times G times cosine 30 degrees, plus X times mass of the firefighter times G times cosine 30 degrees, plus 0 equals 0. So in a lot of these problems, we see that we have an L in every single term and they cancel. That's not true for this problem. We have an L here, but no L here, so they don't all cancel. So be careful not to cross out those L's. That can get you in trouble. So why don't we have a look at what we have here and see what can we solve. We don't know X and we don't know the normal force at the wall, so we're a little bit stuck right here. We can put in some numbers, like we could put in our L and our M and our G here, and we could get a number here and a number here. But we're really kind of stuck until we find this normal force with the wall. So let's just say that we don't know this one, and we need this one in order to find X. So let's ask, how can we find the normal force at the wall? Let's look at our table again. Our normal force at the wall is part of our X component of forces. So when we do the sum of the forces in the X direction, it has the normal force of the wall. So let's write down that equation and see how far it takes us. So the sum of the forces in the X direction equals mass times acceleration in the X, which is going to be 0 because it's not moving. So normal force at the wall minus mu s times normal force with the floor, because that's what our friction is, equals 0. So our normal force with the wall is equal to mu s times our normal force with the floor. Mu s is okay, that's 0.25. Normal force with the floor, we don't know that one. So now we're stuck again. So let's ask, can we find the normal force with the floor? Let's look at our table again. So in the y direction, all of these forces have to sum up to be 0 because it's not moving. We do know the mass of the ladder. We do know the mass of the firefighter. So we should be able to find out the normal force from the floor. Then we can start to work backwards. With the normal force from the floor, we can find the normal force from the wall. With the normal force from the wall, we can find the height of the firefighter. Okay, so let's get going on that y equation. So the sum of the forces in the y direction equals mass times acceleration in the y direction. Because the ladder is not moving up or down vertically, then the sum of those forces has got to be 0. Let's fill in all of our forces in the y direction. We have minus mass of the ladder times g, minus mass of the firefighter times g, plus the normal force of the floor equals 0. Let's solve for normal force of the floor equals mass of the ladder times g plus mass of the firefighter times g. The mass of the ladder is 20 kilograms, so 20 kilograms. The mass of the firefighter is 80 kilograms, and then they're each multiplied by g, 9.81 meters per second squared. So our normal force at the wall, our normal force at the floor is 981 newtons, because we get 100 times 9.81. There's our normal force at the floor. So now, let's start to work backwards. Now that we know the normal force at the floor, we can find the normal force at the wall. So normal force at the wall equals mu s times normal force at the floor, 0.250 times 981 newtons to get 245.25 newtons. We won't round off here because we don't want to make any rounding errors. Now that we know the normal force at the wall, we can plug it into this equation. So minus L times the normal force at the wall times cosine 60 degrees plus L over 2 times mass of the ladder times G times cosine 30 degrees plus X times mass of the firefighter times G times cosine 30 degrees equals 0. So we're coming back to this equation. Let's see what we can plug in here. The ladder has a length of 12 meters. The normal force at the wall is 245.25, and cosine 60 is cosine 60. So if we do this bit in the calculator, this number is 1,471.5. The next bit, L, is 12 meters. Mass of the ladder is 20 kilograms. G is 9.81, and cos 30 is cos 30. So we can do this in our calculator. We get 1,019.5. Then the last little bit, X times mass of the firefighter times G times cos 30. We know the mass of the firefighter is 80 kilograms. So we can do this bit in our calculator, get 697.7. Those things added up have to give us 0. So X times 697.7 equals 1,471.5. This one is negative, becomes positive when we take it to this side. This one's positive, becomes negative when we take it to the other side. Then we divide both sides by 697.7 to get our answer. And that answer turns out to be 0.665 meters. Think about our answer a little bit. It says that the firefighter can only go 66 centimeters up the ladder. I would definitely say that that's not very high. So if we ask what's going on here, because that's not quite an answer we expected, I would wonder if maybe this is not that realistic an interpretation of perhaps the friction between the floor and the ladder, and as well we would have friction between the floor and the wall, so that would change the problem a little bit as well. So there's probably the fact that this is not a very realistic interpretation of a firefighter climbing a ladder, which gives us not a very realistic answer, but it's always good to try and think about your answer. What did you get and why?